Drop your attendance in the chat box. Good afternoon, everyone. Let's continue with module 5, that is synchronous generator. All right. So far we have spent about 2 classes for synchronous generator. So far we looked at the conceptual aspects of synchronous generator, followed by an expression for EMF, the expression for frequency of induced EMF. All right. So today, let us take a topic called EMF equation. EMF equation of synchronous generator. EMF equation of a synchronous generator. Now, in the EMF equation, let us consider the same setup which we had considered while deriving the expression for frequency. All right. So consider an alternator consisting of a single stator slot having a single conductor. Consider an alternator having single stator slot with one conductor. And also consider a 2-pole rotor as shown in the figure. North and south. Also consider a 2-pole rotor as shown in the figure. Okay. And let us define the following. Okay. Let Z phase is equal to conductors per phase, number of conductors per phase. All right. And let us also consider the speed at which the rotor, okay, so this is your 2-pole rotor. Okay, why 2-pole? Because you have one north pole and south pole. So together, you can say that, we have 2 magnetic poles or a pair of poles. All right. So let n be the speed of rotor. Okay. You can also call it as synchronous speed. Okay. Why synchronous speed? I have already told you, because the rotor always runs at a fixed speed. Okay. And say phi is equal to flux per pole, and let's say what else? F is equal to frequency generated EMF. Okay. And P is equal to number of poles. So what we have done, we have defined the machine constants. Z phase, conductors per phase. N is speed of the rotor. Phi is flux per pole. And F is frequency of generated EMF. All right. And P is equal to number of poles. All right. Okay. Okay. Then you can say that the frequency of induced EMF can be given as F is equal to Pn divided by 120. Okay. So we have already derived this particular expression in the previous class. So those who have missed, they can refer to lecture 2 of module 5. So induced EMF frequency is F is equal to Pn by 120. Okay. Next. Now, when this rotor, starts rotating, what happens is that the north pole cuts the conductor as well as the south pole cuts the conductor. So you can say that in one revolution of the rotor, once the north pole cuts the conductor and once the south pole cuts the conductor. So due to which in one revolution, one cycle of EMF is generated. All right. Okay. Now, the flux cut by, okay, next you can start. The flux cut by P poles. Okay. No, instead the flux cut by the conductor in one revolution of the rotor is equal to the flux cut by the conductor in one revolution of the rotor is equal to flux into number of poles. Okay. So if you have two poles, it would have been 2 phi. Okay. So what we have considered a general machine in which we have assumed there are p number of poles, because if you consider p number of poles, then in your ultimate EMF expression, what you have to do is just replace the value of p with the appropriate number. Okay, so that being the objective, what we have done is we have considered a p-pole machine. So flux cut by the conductor in one revolution of the rotor is equal to 5, which is nothing but flux per pole, into the total number of poles. Okay, so it is P5 Webers, and it is also can be taken as change in flux d5. So flux cut is nothing but change in flux d5. All right. So that's your first observation, which is taken from the operation of alternator. Okay. I hope you have noted down equation number 1. Okay. Next. Let us try to estimate what is the time taken to complete one revolution. Okay. Next, you can write time taken to complete one revolution of the rotor. Okay. So let us call this time as dt. Okay. Now you know that the rotor is rotating at a speed of n rpm. Okay. So n rpm, revolution per minute. So in terms of second, you can say that n revolutions are getting completed in 60 seconds, right? N revolutions are getting completed in 60 seconds. So what is the time taken to complete one revolution? Okay. So that is your dt. So what do you get when you cross multiply? So when you cross multiply, you will get dt as 60 by n second. 60 by n second. All right. Then, as per Faraday's law of electromagnetic induction, Faraday's law of electromagnetic induction, EMI stands for electromagnetic induction. The average value of induced EMF, say E average, is equal to, okay, let me consider the modulus. Okay, modulus. Mod E average is equal to n into d phi by dt, right? Which is equal to, okay, how many conductors did we consider? We considered a single conductor. All right. So n is equal to 1. So n is equal to d phi by dt, or it is simply rate of change of flux. Rate of change of flux. Okay. So take this as equation. Okay, this is equation 2. Okay, and you can take this as equation 3. Okay. Now I think you must have understood the objective behind finding out discretely what is d phi and what is dt. So d phi we got it as p into phi, right? And dt we defined it as time taken to complete one revolution, and we have equation 2 for dt. Okay, now what you can do, you can just substitute equation 1 and equation 2 in equation 3. All right. So next you write substitute equation 1 and 2. Okay. Now just a small clarification. Did we give any name for equation 2? That is p phi. Did we write any equation number for p phi? I think we haven't written, right? Nevertheless, you can take that p phi is equal to d phi as equation 2. Okay, and this you can take it as equation 3, and this you can take it as equation 4. Okay, then you can write substitute equation 2 and 3 in 4. Please make a note of it. Okay, substitute equation 2 and equation 3 in 4. So what do we get? When we substitute, we get the average value of induced EMF. So you can write E average is equal to d phi. What is d phi? D phi divided by dt. What is dt? 60 by n. So if you rearrange, what do you get? You get p phi n divided by 60. Okay. So let's call it as equation 5. Equation 5. Now, in equation 5, you can do some substitution for speed n, right? So which relation can give me the expression for speed? Equation 1. So we had written, so you can say that from equation 1, okay, what is equation 1? It's a frequency relation. F is equal to Pn divided by 120. So that implies n is equal to 120 F by P. Just cross multiply and rearrange the equation. So we get the expression for synchronous speed. Okay. Now substitute 6 in 5. Substitute 6. That is, in place of n, you substitute 120 F by P. So what do we get? We get V average is equal to P into phi into n. N is 120 into F divided by P into 60. Right? So simplify. So what happens is that PP gets cancelled and 60 goes 2 times, and then you will have 2 pi F volts. So this is your average value of the induced EMF. Okay. So say 7. Equation 7. All right. But you know that in our day-to-day life, nobody talks about the average value or the maximum value. We talk about the RMS value. So let's try converting this average value into RMS value. So we have the form factor expression, right? For a sinusoidal wave, we have form factor as RMS value to the average value. Okay, and what is the form factor for a sinusoidal wave? It is 1.11. So from this you can find out the RMS value. So RMS value is basically 1.11 times the average value, right? So from the above expression, we can say that the RMS value is 1.11 times the average value. Okay. So substitute. So therefore, ERMS, or simply capital E, is equal to 1.11 into the average value. What is the average value? 2 phi F. 2 phi F. Or E is equal to 2.22 phi into F. Say equation 8. Okay. All right. So this is the expression for induced EMF, that is RMS value of induced EMF in an alternator. Okay. But this is not the complete EMF expression. That's because how many conductors did we consider while deriving the expression? We considered one single conductor, right? But in your real alternator, you will not have a single conductor. Instead, you have multiple conductors, right? You can recall the construction of stator, right? So while explaining the stator construction, I had placed the conductors all around the periphery of the stator. So there are many conductors. Okay, in a big machine, the conductors may be as high as 2,000 conductors, 3,000 conductors. Okay, so therefore, you can say that equation 8 represents the induced EMF, in one single conductor. One single conductor. On the other hand, while deriving the expression for EMF equation, we have assumed there are Z phase conductors. So therefore, induced EMF in Z phase conductors is equal to, E is equal to, this is something like very simple. So in one conductor, induced EMF is E. So in Z phase conductor, what is the value of induced EMF? So what is it? Z phase into E. So where is E? E is 2.22 phi into F into Z phase. That's all. So you have to just multiply equation 8 with Z phase. So it is 2.22 F phi Z phase. Okay. So this is your induced EMF in a alternator. All right. Fine. So that's the expression for induced EMF, and say equation 9. Equation 9. Now, equation 9 represents the ideal equation for EMF. Equation 9 represents the ideal EMF equation of a synchronous alternator. Okay. Now, equation 9 is derived. On the following basis. Okay. Nowhere I have mentioned about the type of winding. Now, you see, in AC winding or in AC machines, it is not that you place the conductors in an erratic manner. No, you can't do that, right? Because to get a balanced AC voltage, you know that the conductors are placed in such a way that R phase conductor, Y phase conductor, and B phase conductors are placed in such a way that the induced EMFs in them are 120-degree phase apart. All right. So the equation 9 represents the most ideal equation, which may not be, valid in the real or in a practical machine. That is due to the following two reasons. The first reason is that equation 9 is being derived by assuming full pitched winding. By assuming full pitched winding. Don't worry, don't bang your head for this. I'll explain you. Okay. Anyhow, we don't have to dig deep about full pitched winding because in 6th semester you have a separate course on design. All right. So we have assumed full pitched winding, and we have also assumed distributed winding. So you can say that we have assumed concentrated winding. Concentrated winding. But in a practical machine, the winding is not full pitched. So converse statement I'm going to write. This is only for an ideal machine, for the sake of explanation. For a practical machine, the winding is not full pitched. Instead, the winding is, instead of full pitched winding, the winding, in short, let me write, the winding is short pitched. The cricket terminology, short pitch delivery, they say, right? So winding is short pitch instead of full pitch. Okay. Then instead of concentrated winding, okay, this I will explain first. Concentrated winding. Concentrated winding in the sense, what we are assuming is that all that Z phase conductors are concentrated in one particular slot. Let me repeat. All Z phase conductors are concentrated in one particular slot. So that is called as concentrated winding. But do we do it in our actual machine? No, we don't do it because you have these slots all around the outer periphery of stator. So conductors are distributed evenly in all the stator slots. That is the reason we say that in a practical machine, instead of concentrated winding, we have a distributed winding. So instead of a concentrated winding, we have a distributed winding. Distributed winding. All right. So this short pitched and this distributed concept is called as winding factor. So by incorporating the winding terminologies, as in short pitched winding and distributed winding concept, the final EMF equation of an alternator is given as E is equal to 2.22 F5 Z phase multiplied with the two factors. One factor relates the short pitch concept and the other factor, represents the distributed winding factor. So those two factors are taken as Kp and Kb. This is your final equation of induced EMF in an alternator. Okay. We also have a relationship. Z phase is 2 times T phase, where T phase is equal to turns per phase. Okay. 20 turns, 40 turns, the winding turns. Okay, so this T is nothing but the turns, the winding turns. So a conductor is made up of 2 turns. Okay, so Z phase is equal to 2 T phase. So in terms of number of turns per phase, your EMF equation E can also be written as, so Z phase you will replace with 2 times T phase. So 2 into 2. So 4.44 you will get Kp, Kd, F by T phase. All right. So while solving problems, you can either consider the EMF equation in terms of Z phase, or you can consider EMF equation in terms of T phase. Doesn't matter. All right. So this is your EMF equation. Very, very important. All right. So after writing down the ideal equation, you have to talk about the practical alternator. So in a practical alternator, winding is not full pitched. Instead, it is short pitched. And in a practical alternator, the conductors are not placed in one particular slot. Instead, the conductors are distributed in the adjacent slots. Hence, in a real machine, we have a distributed winding. So by considering the short pitched winding and a distributed winding, you can write down the final expression for EMF as 2.22, the winding factor Kp into Kd into F into phi into Z phase. Okay, so this is about the EMF equation. So if you have any doubts in the above explanation, you can ask me. Okay, so if you don't understand, okay, what you can do, you can replay the video and you can make an attempt to understand. In spite of that, if you don't understand, please fall back. All right, you can ask me. So okay, so we discussed about the short pitch winding and the distributed winding, right? Now, what exactly this short pitched winding is all about? Okay, so you can just write a short note. Okay, I'm not going to draw any or derive any mathematical relation, only a qualitative discussion. Okay, qualitative discussion in the sense, orally I'm going to say about the winding factors. Okay, then you can write this qualitative discussion on winding factors. Qualitative discussions on winding factors. Now, winding factors, as you have seen, winding factors, there are two types, right? One is Kp and the second one is Kd. This Kp is called as pitch factor. Kp is called as pitch factor. Sometimes this Kp is also called as coil span factor. Coil span factor. They are different names. All right. On the other hand, Kd is called as, right? It is distribution factor. Or you can also call it as breadth factor. Breadth factor. There are different names for it. Okay. Distribution factor, breadth factor, cording factor, etc., etc. Doesn't matter. Okay. Now, first let us look at what is Kp. Kd is pretty simple, right? You can just go with the dictionary meaning. Distribution means winding distribution in the adjacent slots. That is Kd. Okay. Now, Kp is slightly complex. So what I will do, I'll try to keep the explanation as simple as possible. All right. To understand Kp, okay, first let us consider Kp, that is pitch factor. Let us consider the two pole pieces, one north pole and one south pole. Okay, one north pole and one south pole. Next, what you can do is you can draw imaginary line from the center of each pole. Okay. From the center of each pole, draw an imaginary line. Okay. So the distance between these two parallel lines is called as the coil span. Okay, coil span. Here, let me mention. Coil span is nothing but the distance between the centers of two adjacent poles. Okay, this is coil span. Okay. Now, for a full pitched winding, the designer will keep one turn here and the other turn exactly at the center of the south pole. The distance between the two coils. Okay, so this is coil 2. Let me write. This is sorry, instead of coil. Turn. This is turn 1. And this is turn 1. Turn 1 and turn 2. All right. Or coil or one ends. Now, when you place one coil such that if it is coinciding with the center part of north pole and the center part of south pole, okay, then we call it as a full pitched winding. Okay. Now, the distance between the two coils or turns, okay, coil. You can also say coil. Okay, is called as coil span. I've already mentioned. And distance between the centers of two poles, you can call it as pole pitch. Pole pitch. Okay. So for a full pitched winding, pole pitch is equal to coil span. Pole pitch is equal to coil span. And this is how the two coils or turns are connected. This is how the two turns are connected. And the triangular shape is called as end connection. Okay. So the turns as well as end connections, they are all made up of copper. So copper is used for constructing the winding. Okay. So this is about a full pitched winding. Okay. So the two turns are placed such that they are coinciding with the centers of the north pole as well as south pole, due to which the distance between the pole and the coil span becomes equal. All right. Now, in case of short pitched winding, what they will do is the second turn they will not keep in line with the center point of south pole. Instead, it is kept at a shorter distance. So instead of placing it here, in case of a short pitched winding, that particular coil is intentionally placed with some offset distance, with some offset value. Okay. Now, by doing so, what you can achieve is that you can achieve the smaller end connection. So this is also end connection. All right. I'll write it here so that you will be able to see it clearly. So this is also end connection. End connection. Okay. Now, if you compare the lengths of two end connections, you have two end connections, right? The first end connection is for full pitched coil, and the second end connection is for short pitched coil. Okay, let me complete this. This is your coil span 2. Okay, this is your coil span 1. You can clearly observe that in case of short pitched winding, this is your short pitched winding. Okay. In case of short pitched winding, coil span is less than the full pitched winding coil span. And also, one noticeable difference is that the end connection is smaller for a short pitched winding. For a full pitched winding, you look at the length from here to here, the red line. On the other hand, if you look at the short pitch winding, you can see that the end connection is very, very small. Now, this end connection is just meant for connecting the two conductors. Okay, and these end connections do not take part in EMF induction. It just provides that support for the winding. So that's the reason, if you can limit the usage of end connection, you can limit the copper usage, right? By limiting the copper usage, you can achieve a cost-effective machine design. So for the sake of saving revenue, or for the sake of cost effectiveness, instead of full pitched winding, a short pitched winding is employed in a real machine. All right. So in order to save copper in the end connection, instead of a full pitched winding, a short pitched winding is used in case of a practical machine. So that is the first advantage of the short pitched winding. The second advantage of short pitched winding is that the shape of the induced EMF remains close to sinusoidal shape. So the shape of the the shape of the induced EMF remains almost sinusoidal. So it gives a better wave shape with a short pitched winding. With a full pitched winding, the wave may not be purely sinusoidal. So you can also correct the wave shape using a short pitched winding. Okay. So in exam they may ask a short notes on full pitched winding and short pitched winding. Okay. They may ask something like, what is the advantage of a short pitched winding? The advantage of short pitched winding is, first of all, it can save copper in the end connection. By saving copper, we can achieve cost-effective machine design. The second advantage is that with the help of short-pitched winding, the wave shape of the induced EMF remains almost sinusoidal. So that means to say, it also helps in eliminating so-called harmonics. Okay, so that's the advantage of a short-pitched winding. Next, you have distributed winding. KD. I won't spend much time here. In a practical machine, winding is not concentrated in one particular slot. Instead, winding is distributed in the adjacent slot. Hence, the winding in a real machine is called as a distributed winding. Okay. Now, short pitched winding or sorry, not short pitch winding, the pitch factor Kp. Okay, this is pitch factor. Pitch factor Kp. This pitch factor Kp can be found analytically using the following formula. Okay. Cos of beta by 2, where beta is equal to chording angle. Chording angle in degrees. Okay. So Kp is equal to cos of beta by 2, where beta is equal to chording angle in degrees. Then Kd can be found using the following formula. M sin alpha. Kd can be found using M sin alpha by 2 divided by okay, so this formula. So this Kd, sometime later, I don't recall the formula. It is sin n alpha by 2. Yeah, no, I recall sin n alpha by 2 divided by n sin alpha by 2. All right, so this is the formula for Kd. Okay, so that's what I was mentioning. There is no derivation. You will have to just by heart this formula, okay, because it takes a lot of time to derive, and in the introductory course, the derivation is not included. Okay, so Kd is equal to sin n alpha by 2 divided by n into sin alpha by 2, where alpha is equal to slot angle, which can be found as 180 degree divided by 3 n. 180 divided by 3n, and n, everywhere we have written n, right? N is equal to slots per pole per phase. Okay. Very simple to understand. When we take numericals, you will be able to understand, okay, in a better way. So number of slots divided by poles divided by phase. So that is the understand. All right. So when we solve problems, you will be able to understand how exactly we calculate Kd and Kp. Okay. So Kp is cos beta by 2 and Kd is sin n alpha by 2 divided by n into sin alpha by 2. All right. And Kd can also be defined as the ratio of the induced EMF in a concentrated winding to the induced EMF in a distributed winding. Okay. That is the definition of Kd. Okay. Fine then. So that is about the winding factor of an alternator. Okay. So that's it. So that is about your synchronous generator. It's a short module. So we are done with module 5A, that is synchronous generators. All right. So now we are left with only the problems. So I think I can take up the problems in the next class. All right. So if you have any doubts, you can discuss. Okay, I'll stay for say 1 or 2 minutes. If you have any doubts, please discuss. If you don't have any doubts, probably you can drop off now. Okay. Thank you.